Morning, Bill here. This is computer science. Let me make sure everything's computer science 221. And what we're going to be talking about in these lectures here today, there are a couple of short videos I'm putting together. We're going to be talking about representing floating point numbers. So I want to make a couple of distinctions here um, that we haven't made previously. When I write something down like this, um, no decimal point there, that's an integer. Likewise, minus 17, 23, these are all integers. But if I come over here and I write this down, 3.0, this is now a floating point number, an FP, FPN. Likewise, so would minus 7.562, anything where I see a decimal point there. And we skipped over it in the book, but we're coming back to it now because we're curious about how numbers like this are stored internally. And it turns out that the representation for this number here is going to look very, very different than the representation for this number here. What we're going to be talking about is what's called an IEEE floating point standard. I just mentioned this for completeness. You don't have to remember this name. The IEEE is the International something or other. I've got their web page right here. IEEE. This is where engineers meet and do their thing. Something about engineering and electrical something or other. Very big international group. They set lots of standards. They had to do with lots of the protocols that are developed on the internet. And they established this floating point standard. And in fact, they came up with two of them. They came up with a 32-bit standard, and they also came up with a 64-bit standard. And again, you may recall that in Java, when we say float, in fact, it is a 32-bit quantity. And when we say, let me see, I believe double, it's a 64-bit quantity, both representing floating point numbers. We're going to take a look at this standard. And at first, it's going to seem kind of strange, and I'm going to try and break this up into pieces. But here's what it looks like. There are 32 bits and it's broken up into a bunch of pieces. So there is one bit over here, and then there's 1, 2, 3, 4, 5, 6, 7. There are 8 bits over here, and then over here there are 23 bits. So there is 1 bit here, there are 8 bits here, there are 23 bits here, and 1 plus 8 plus 23 is in fact equal to 32. And this bit right over here is the sign bit. So that one's really easy. 0 means positive. 1 means negative. This thing over here, these 8 bits, are called the exponent. And these 23 bits over here are called the mantissa. And it's here that's going to take some explanation. So just file this piece of information away here, but let's talk about something else. I want you to recall, right, I think it was the first day of class, we wrote something down like this. We wrote 237, and we said, gee, we could think of that number as being a 7 times 10 to the 0. And this over here was 3 times 10 to the first. And this over here was 2 times 10 squared. And then we just added all of these up. So that would be 200 plus 30 plus 7. Well, what I'd like to do now is I'd actually like to extend this to something else. Let's think about the following. If I were to write down 23.49. Now again, this 3 is 3 times 10 to the 0. And this 2 here is 2 times 10 to the first. But now this 4 here, this is 4/10. This is 4 times 10 to the minus 1. And this 9 over here is 9 times 10 to the minus 2. So notice we have this very nice pattern here. The decimal point was right here. And to the left of the decimal point, we're going into positive integer territory when we look at the exponent. When we go to the right side of the decimal point, we just start getting numbers that get smaller and smaller. So we can very much extend this if we want to binary numbers. If I were to come over here and I were to write a number down that looked like this, okay, this is, I'm sorry, that's 1 times 2 to the 0. That is 1 times 2 to the first. That is 0 times 2 squared. That is 1 times 2 to the third. But now I come over here. That is 1 times 2 to the minus 1. That is 0 times 2 to the minus 2. 1 times 2 to the minus 3. So let's think about what this is. 1 times 2 to the 0 would be a 1. 1 times 2 to the first would be a 2. 0 times 2 squared would be a 0. 1 times 2 to the third is an 8. This over here, 1 times 2 to the minus 1, that's 1/2. This is 0. This is the same thing. Remember, 1 times 2 to the minus 3, this is the same thing as saying 1 over 2 to the third. Well, that's 1/8. So this is equal to 8 plus 2 plus 1 plus 1/2 plus 1/8. And that's equal to, well, 8 plus 2 plus 1 is 11. It's funny because that's a base 10 number. I'm not talking about a base 2 number here. But 1/2 plus 1/8, well, that's equal. Remember, 1/2 is equal to 4/8. So this is 5/8. Everybody okay with that? Let's try another one. If I were to say 1001.0101, okay, again, you could do, this is 1, 2, 4, 8. This is 1/2. This is 1/4. This is 1/8. This is 1/16. So this is equal to 8 plus 1 plus 1/4 plus 1/16. And that's equal to 9. 1/4 is 4/16 plus 1. This is 5/16. So this number here is equal to 9 and 5/16. Okay? I hope this is easy. Yes. Okay. Now, let's consider something else. So if I come down here and I write a number like this, if I write 567.123, we know that that's 567.123 times 10 to the 0th power. Remember, anything to the 0th power is 1, so I'm just multiplying by 1. But there are many alternative ways that I could write this. This is also equal to 56.7123 times 10 to the first, which, by the way, is also equal to 5.67123 times 10 squared, which is also equal to, and we can do this for quite a long time. I promise we won't. But notice I can actually even go the other way. It's also equal to, so here the exponents are getting bigger, but it's also equal to 5,671.23 times 10 to the minus 1. And it's also equal to 5,671.3 times 10 to the minus 2. And this could go on forever and ever and ever. Well, the point is we need to agree which one of these do we want, okay, for storing inside the computer as a floating point number. And the answer is we're going to pick this one right over here. And the reason why we pick this one right over here is there is exactly one digit to the left of the decimal point. And in starting off with this and getting it into this form over here, we're going to call that normalizing. Okay, so again, the same thing happens when we're working in binary. So for example, if I had this number here, okay, now remember, this is 1, 2, 4, 8. Oh, I picked that goofy 11 again. Let's put another one here. So that's now 16, and this is 1/2, and this is 1/4, and this is 1/8. So this number here is really, this is 16 plus 8 plus 2 plus 1 plus a 4th plus an 8. So that's 24, 26, 27. So this is really 27, and this would be 3/8. But this number here, 11011.011, is actually this times 2 to the 0, which is equal to 1101.1011 times 2 to the first, which is equal to 110.11011 times 2 squared, which is 11.011011 times 2 to the third, which is equal to 1.101101 times 2 to the fourth. And notice that this is now normalized. And it's normalized again because there is one non-zero digit to the left of the decimal point. So this is normalized. Okay? Just to give you another example. Suppose I had this. Okay, now this is not normalized because this over here is not 0. Or this is 0. We have to get a number there that's not 0. So this is times 2 to the 0. Okay, now what I need to do here is I need to come over here and go, well, that's equal to 0.001 1101 times 2 to the minus 1. And that's equal to 001.101 times 2 to the minus 2. Okay, I think I'm recording. I am recording. Okay, good. I paused it for a second. So we can see over here that basically that if we move the decimal point to the left, the numbers go into the positive territory. We saw that on the last number. Okay, as the decimal point went this way, these numbers got bigger. On the other hand, as the decimal point goes to the right, we go into negative territory. But the point that I want to make is that we had this number here. This one down here is the fully normalized representation. Okay? Easy so far? Okay, so here are some exercises. Where I'll say the following. Rewrite the following as normalized binary floating point numbers. So I'll come over here and I'll say A, and why don't we make this 23.875. Why don't we say B, 0.125, C, I don't know, 31.75. And I'm going to stop the tape for a second so I can take a sip of coffee. But you should work on these right now, and so you should stop the tape as well, and then we will come back and we'll do these three.